on a number generating cube, people call it die, plural, die, the singular version of dice. I worked in a school where we had to call them number generating cubes because dice meant gambling. So we called them number generating cubes. How many even numbers are on a dice, on a die?
3.
There's 3. So the probability of getting an even number when you roll a die is what? 3 out of 6, which would reduce to 1/2. Even and odd is always half. It always reduces to half. Because you're either an even number or an odd number. Okay? And so that's my personal definition of probability, is just correct over total. And number of ways that the event E can occur versus the number of possible outcomes. This E means the event. This S means the sample space. What we get when we're talking about probability is a lot of times we'll say, this is your set of numbers or your sample space. We don't care about all the numbers in the world. We only care about these 4 or these 8 or these 12, which is great for you as a student working the problem, because it's a lot better to deal with 12 numbers than an infinity amount of numbers. Okay. We have disjoint events. Disjoint is the opposite of joint. So think like a joint banking account. Disjoint would be separated. Like disjoining Siamese twins. Disjoint, separate. Okay. And so that's what disjoint event is. And then general rule for addition, we use this one. Disjoint, when the events are disjoint, this is like the addition rule. General addition here is when we have non-disjoint or overlapping events. So that's the difference between the two. Because these are disjoint, so they don't have an and. These are overlapping, so they do have an and. We'll go into greater detail of that later. All right. These formulas, chapter 6. I know I'm talking about chapter 6, or sorry, this is still chapter 5. Some of these are the ones where we start using them algebraically. This one is the one that's definitely used algebraically. These can be done in the calculator. Do you know where that button is? The exclamation point? You can find it. So I know that a lot. So push the math button. Now you have math, number, CPX, and PRV. PRV is probability. So you can hit right 3 times, or you can hit left once. Okay? And what's great about this screen on your calculator is your first option is RN. You don't use that one at all. Okay? The second option is NPR. That's this one. Third option is in CR, which is this one, and then your fourth option is the exclamation point. So this is where you'll go to get there. And that's pretty much all we use from this screen. It's option 2, 3, 4. Those are ones we use a lot in chapter 5. Outside of chapter 5, we don't go back to those. It's really just chapter 5. All right, these are very complicated formulas. They take a lot of work to do. I will do it one time by hand, and then I will just use the calculator the rest of the time. This one is one that can't be done in the calculator, so you have to know how to put a fraction in your calculator and how to do use the exclamation point, which is factorial. Factorial is fun. It's in factorial. So all factorial is you say a number like 6, that just means 6 times 5 times 4 times 3 times 2 times 1, which is 6, 24, 120, 720. I used to have students when I taught high school, and they'd be like, the answer is 5. And I'm like, no, it's not. Because that means 5 times 4 times 3 times 2 times 1, which is 120. I've always wanted to go get a job and say, I want to get paid this much an hour. What did you calculate? Push 10, and then go to your math probability, and then put it in.
Boom.
And what do you get?
36,000.
Wait, one more time. You can just read the numbers. You don't have to tell me what it is.
362.
362.
88
All right, so that's 3.6 million. Right? That's all I want to get paid an hour. Not work for 1 hour. So if you're doing your own contract, just sneak in a little exclamation point. It's not happening.
I'm gonna get fired right away.
What that?
I'm gonna get fired right away if I did that.
But then you can sue them and say, no, you agreed to this amount. And they have to pay you.
Well, that's a good.
For 2 hours that you work. No, that won't happen. Alright. Chapter 6. Other formulas. This right here, we get done, we do all this using list 1 and list 2 as our frequency. That's done pretty quickly. Standard deviation of a random variable. Again, we can use this using one variable statistics. This is one that some people figure out how to do it on the calculator. Some people do it by hand. It's kind of like dealer's choice. There. Mean, again, we do these by list 1, list 2. There are some times where you have to do this one by hand. Sometimes I think doing it by hand is easier. We don't really deal much with this one or that one. Alright, so those are our formulas that we gotta do. So chapter 5 is very formula heavy, so make sure you do know those formulas. Alright. Now, probability. This is where you as a student, to be more successful, you need to be comfortable going between a percentage and a decimal. So when we talk about probability, we have an impossible event. That'd be like 2 people having a baby and them having a dog. That's an impossible event. Okay? We have a certain event. So that'd be like 2 people having a baby and it being baby. That's a certain event, which is at 1 or 100%. And then we have these things that an unusual event. So this would be less than 0.05 or less than 5% chance. So that would be like passing this class without doing homework. That's an unusual event. Less than 5% chance of happening. Alright? That would be like having octuplets. That is a less than 5% chance of happening. What's that? Octuplets. 8 babies. Alright? Not so unusual. Well, if an unusual event is less than 5%, a not so unusual event would be more than 5%. That not contradicts it. Alright. So, whenever you're given a chart about probability and they ask, hey, is anything wrong with it? You need to see, is everything between 0 and 1? This is one of those things that I hated as an athlete when I was younger. I'd have coaches go out there and give me 110%. I'm like, coach, it's impossible to get more than 100%. And then I use that so much.
Did you learn your lesson at some point?
No, I kept arguing it. It's impossible to get more than 100%. You can only give the max of 100%. If the coach is telling people to give 110%, that means there's people on the team only giving 90%, and he wants them to give more. If you give 100% every time, it's impossible to do more than 100%. All right, check your probabilities. If anything, if they have negative probability doesn't make sense. There's a negative 10% chance this event will happen. No, we don't have negative probability. Probability is always positive and always between 0 and 1. And then the sum of all the probabilities should equal 1. When I look at data, and there'll be like 40% of people voted for this person, 30% voted for this person, and 20% voted for this person. And I'm like, that only adds up to 90%. Where's the other 10%? No, because when you talk about voting, it's all the people who voted. So the 10%, it's like, where's this data? Serious. I worked somewhere and we had these like charts, and it showed like passing rates for classes, and the chart went up to 120%. I stopped listening to that presentation. Because it's impossible to have a class have 120%. So why even have that as on a chart? Because my number at like 90% passing was nowhere near the top of the chart, which is 120%, which could never reach. And I asked the presenter, and she got really mad. I'm like, you put data that...
You probably didn't think you'd ask.
You put data that doesn't make sense. All right, so when you look at the probability right there in problem 2, very obvious, you can't have negative 0.2% probability. Here, a list of data. 0.23, that's 23%. 1.47, that's 147%. So that does not make sense. 0 makes sense. Negative 0.52 or negative 52% doesn't make sense. 0.05 makes sense. 1 makes sense. All right. Now, when I was in my statistics class, we had to make these probability trees. And we had to draw them out and do it, and I think it's very useful. So in number 4, it says, if a person flips a coin and then spins a spinner that has 6 spaces on it, describe the sample set. So for me, I always go back to my probability tree. So we have a coin, and then we have a spinner. So here is the event. You have heads or tails. But then we have 1, 2, 3, 4, 5, 6 outcomes. 1, 2, 3, 4, 5, 6 outcomes. So when you look at all possible outcomes, you have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. So you can see that there are 12 possible outcomes. And so creating this probability tree makes it easy for you to identify what's going on, and then of course make sure you don't miss anything. All right, what's the probability of it being impossible? That would of course be 0. Suppose the probability is approximated to 0 based on empirical results. Does this mean the event is impossible? Approximately 0 is not the same as impossible. It needs to be exactly 0 to be impossible. You know, the probability of winning the lottery is like 0.000006. You know, it's not impossible to win the lottery, but it is we use the term improbable. Alright. If you play a card game 100 times and you're dealt the hand exactly 35 times, what does this mean? Well, 35 out of 10 is 35 over, or 35 out of 100 is the exact definition of probability. Percent means out of 100. So if you're doing 35 out of 100, that's 35%. We can look at that as 0.35 as the decimal, or 35%. Probability is a measure of the likelihood of random phenomenon or chance behavior. That's the definition of probability. Alright. Important vocabulary terms. An experiment is any process that can be repeated where the results are uncertain. That uncertain is what makes it an experiment. If you know if you flip heads and it's going to get heads every time, that's not an experiment. I had a friend's dad who had a coin that said, heads I win, tails you lose. And he would flip that coin and be like, oh, heads I win. Flip the coin, oh, tails you lose. And he would do that whenever his children would want to go out. He's like, oh, that's the coin. Oh, heads I win, you have to stay home. I never found that coin. I always thought it was hilarious. Not because it wasn't my dad. Alright, sample space. The collection of all possible outcomes. So over there, that process tree at the very end, that's the sample space. Those are the only possible outcomes that we can have. An outcome, result of an experiment. So any one of those 12 is an outcome. And then an unusual event, we've talked about that multiple times. And then an event is any collection of outcomes from a probability experiment. So if I did this experiment 4 times, and I got, say, this, that would be my event. And that, sometimes we talk about flipping a coin, and we know it's heads or tails, but if you flip it, a coin 100 times, will it always land on heads 50 times? If you flip a coin 100 times, will it always land on heads 50 times?
No.
No. There are people, super nerdy people, who go out there and they measure coins, and they see which side of the coin is heavier, heads versus tails.
See if that affects it.
Oh, it does.
Mm-hmm.
Because if a coin is heavier on the head side, then it's more likely to land on the tails.
Mm-hmm.
So there are people out there who will tell you which coins land on heads more times than not. It's like, have you ever watched one of the casino games where they have loaded dice?
Mm-hmm.
You've always heard about loaded dice. You know how to make loaded dice? You make one side heavier or one side lighter.
Mm.
And so if you make one side heavier, then the top is more likely to
Coin.
land than another. It's why if you ever go to a casino, it's not like in the movies where you pick up the dice, you put in your hand, you shake on it, you have someone else blow on it. You can't do that at a casino. Because they're worried about people tampering. You pick it up and you throw it immediately. You're not allowed to do all the fancy cool things that they show you in the movies. Alright. So if you toss a coin 100 times and it lands on heads 76% of the time, 76 times, and tails 24%, or 24 times, then we can say, oh, that the probability of landing on heads is 76 out of 100, which is 0.76. Okay. Rolling 2 dice. If you roll 2 dice, here are your possible outcomes, and I listed them all for you. You get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, and all the way down. If you add it up, getting a 2, or snake eyes, is 1 out of 36%. Getting 12, or 6 and 6, is a 1 out of 36% chance. If you go to a casino and you play the game craps, you lose that game when a 7 or 11 is rolled. Unless it's rolled the first time. But 7 as you see, occurs 6 out of 36 times, which occurs more than any other number. Which is why casinos stay in business, because you're more likely to get this than any other number. Do you know the best game in best game probability wise to win at a casino? Right now?
What was it?
Don't know?
Nope.
It's blackjack.
Hmm.
But in blackjack, you lose 51% of the time. That's the best game. Alright. According to a certain country, 43.1% of 3-year-olds are enrolled in daycare. How do we do this? Well, you can take 43.1 and put it over 100, which will give you 0.431. Or, instead of dividing by 100, you can just move the decimal left 2. Because that's how you change something from a percentage to a decimal. Alright, here's what I was talking about, a sample space. So in this sample space, we have numbers 1 through 10. We don't care about any other numbers in the world. We only care about those 10. And then it says, the event occurring is an odd number less than 9. This is where we gotta be very careful when we're talking about the language of math. Less than 9 is not 9. Less than or equal to 9 is not 9 is included. So this is the event of numbers less than 9, 1, 3, 5, 7. There's 4 of them, 4 out of 10 gives you 0.4. A survey of 800 randomly selected high school students determined that 203 play in organized sports. So 203 out of 800 gives you 0.253, but the next number is higher than 5, so we round up and we get 0.254. Okay? Now, we can take that 0.254 and make an inferential statistic and see. So there's another high school that has 1,000 students. We can multiply our 0.254 and we can say that 254 of them are most likely to be organized and play in organized sports. This is where you got to be careful. These are interpretation. You're making predictions. And then this is why we use the term about. You will never see the term exactly. It's not exactly 254. It's about, around 254. Okay? 100 tulips are in a box. 30 of them are red. So 30 out of 100 is 0.3. What probability of them are purple?
40.
30 out of 100, also 0.3. So if 100 tulips were sampled, what would you expect? You expect 30 of them to be red and about 30 of them to be purple. Any Astros fans in the room? None? There's not a single none of y'all watch the Astros? Alright. Have you watched an Astros game? Alright. Have you heard about the shift that everybody talks about?
I've heard of it. I don't
Do you know why they do it? Why they shift and not play in the same position every time? It's because someone took all the data that of the person up to bat and said they are more likely to hit in this spot more than anywhere else. That's what this problem is right here. Number 16. So if you know someone's coming up to bat and you have left field, center field, and right field, and they hit homers, they hit 67 homers. 23 went to right field. 23 went to right center.
8 went to center.
8 went to center.
12 went to left field.
12 went to left center. And 1 went to left field. Okay? Well, when you look at this statistically, where does this person hit a lot of the time?
Right field.
They're hitting here. So as a coach, instead of being your player lined up here, 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 you shift this guy to here, you shift this guy to here, and you shift this guy to right there. Because now they're more likely to hit here, here, and here. And so this person is covering the field of where this person hits 12, 20, 21 times. So this person's covering this 21, this person's covering this 23, this person's covering this 20. And so that's how the shift was created. Except now, people are complaining about it, and they're gonna have a rule in one of the future seasons that the shift won't be allowed. You have to play up your side of the field, no matter what. I think the shift is one of the reasons why I think the Astros won in 2017, whatever year it was. Okay. Here's where I start drawing pictures for you to understand vocabulary. Alright? We use the term disjoint or mutually exclusive. So this is the formula. When we say probability of event E and probability of event F, they have nothing in common. So E or F, probability of E plus probability of F. You add them together. Okay? If two events are not disjoint, that means there's an overlap between them. So to find probability of E or F, then probability of E plus probability of F minus probability of E and F.
Okay.
So I'll give two examples using cards. All right. As a statistics student, there's a basic understanding that everyone in here should understand cards. If you do not grow up playing cards with a standard deck of playing cards, then you need to go print a colored copy of all 52 cards in a deck. All right. How many cards are in a deck? 52. How many are red? These are things that you should know, or at least your math textbook
26.
things you should know. 26. 26 are red, 26 are black. How many are diamonds? 13. How many are hearts? How many are spades?
I don't know.
How many are clubs? How many face cards are there?
52?
12.
52?
Jack, queen, king. 3 times 4 is 12. Okay? These are things that every statistics book expects students to know. But this has been before cell phone. Before cell phone, people used to sit around and play cards. Now we sit around and play on we'll all sit at the same table and play on our own phone and have conversations with each other. That's what we do now. Alright. So, let's look at the probability of getting a heart or a club. So, how many hearts are in a deck?
You say 13.
13. 13 out of 52. And so these are mutually exclusive because hearts and clubs don't have overlaps. Okay? Plus, what's the probability of getting a club? 13 out of 52. So you get 26 out of 52, which is 1/2. Okay? Now, what's the probability of getting a heart or a jack? Okay? How many hearts are in a deck? I already know, it's 13 out of 52. How many jacks are in a deck? 4 out of 52. Now, we can't add these together to get 17, and the reason that is because there's a jack that's a heart. So there's a jack of hearts that is counted here and counted here. So it can't be counted twice. So this is when this formula, we subtract the and. So we have to subtract the 1 jack of hearts. So then we get 13 and 4 This piece is 17 minus 1 equals 16 out of 52, which reduces to 8 out of 26, 8 out of 26, and then that's 4 out of 30. Alright, so that's how these two formulas play out. If there's overlap, you can't have it counted twice. That's why we have to subtract it once. It's not overlap twice. Alright? So that's what these problems are. It asks you to find the probability of E and F. So you add E and F together, and you can see that it overlaps 6 and 7. So these are not disjoint because they are included together. And I showed you here, F contains 5 out of 12, G contains 4